So let's look at expansion on on principle of moments. So for example, let us say you have a uniform bar. A uniform bar means a regularly shaped bar. That implies that the center of gravity of the object will be acting at the middle, and at the middle the weight acts so at the middle, which is the position of the center of gravity, the weight will be acting vertically downwards. So let us say that the bar is pivoted at a distance a from end A of the bar, and also then we have weight F1 acting at distance D from the bar. Distance between the weight and F1, let's say it is B, while distance between the weight and the pivot here, it is C. So let us say you have another weight of F2 at end A of the bar, while we have a force F3 suspended at end B of the bar, which is making an angle of theta to the horizontal. So let us just illustrate the principle of moment. Now A, C, B, D, they are all distances, while F2, W, F1 and F3, they are forces. So according to the principle of moment, if you take the moment about the pivot, the total clockwise moment will be balanced by the total anti-clockwise moment. So you need to state the position in which you are taking the moment about. So I can state this as taking moment about pivot. If I take the moment about pivot, F2 is going to cause the bar to turn anti-clockwise from the pivot. W is going to cause the bar to turn clockwise about the pivot. F1 is also going to cause the bar to turn clockwise from the pivot. F3 is an upward force, so it's going to cause the bar to turn anti-clockwise from the pivot. So these are we have two clockwise moments and two anti-clockwise moments. So we can state it that total clockwise moments will be balanced by total anti-clockwise moments, which is the first thing there. So what are our clockwise moments? W, moment, don't forget, is the product of the force and the perpendicular distance from the pivot. So the moment of W will be what? W times C, product of the force and perpendicular distance from the pivot. The moment of F1 from this pivot will be what? F1 multiplied by the perpendicular distance from the pivot, which is C plus B. This will be balanced by the total anti-clockwise moment, which is F2 multiplied by its perpendicular distance from the pivot, which is A, plus, now F3 is a two-dimensional force. The vertical component of F3 is F3 sin theta, while its horizontal component is F3 cos theta. It is the component of the force whose line of action is acting perpendicularly to the pivot, to the distance from the pivot, that will produce a turning effect. F3 cos theta is acting in a direction that is parallel to the distance from the pivot. Therefore, the moment about the pivot is zero. So this is the only force. This is the component of F3 that will produce the moment about the pivot. So I'm going to write plus F3 sin theta multiplied by the perpendicular distance of F3 sin theta from the pivot, which is what? C plus B plus D. So that is just a simple expression on how to take the moment of all the forces about the point. And when you take the moment of all the forces about the point, you can use that to determine either force or distance. Because in solving problem, if you have a linear equation, that linear equation you can only solve one unknown. So sometimes you'll be solving for force, some other times you'll be solving for distances, as the case may be. But what is important is that you should know how to apply. What do you understand by the center of gravity? Is the point where the weight of an object acts. If the object is regularly shaped, the center of gravity will be at the middle. We have explained that earlier on. Then principle of moment state the algebraic sum of the clockwise moment and anti-clockwise moment taken about the same point is equal to 0. What that means is that the total clockwise moment is equal to the total anti-clockwise moment about the same point. And moment, so we need to, and moment is a vector quantity, it has direction. So you need to identify what forces are producing clockwise moment and what forces are producing anti-clockwise moment about the same point, which is the pivot. So after you've done that, you can put the total clockwise moment, which is the product of each of those forces and their perpendicular distance from the pivot to the left, and is balanced by the total anti-clockwise moment, the product of each of those forces and their perpendicular distance from the pivot. Alright. So having said that, let us take some questions now on the principle of moment. Let us quickly take some questions on the principle of moment. And the first question we'll be looking at is this. A uniform bar of length 2 meters and weight 80 newtons is pivoted at a distance of 30 centimeters from NA. A weight of W newtons is suspended at 50 cm mark from NA. The bar is balanced by a weight of 70 newtons from 20 cm mark place 70 newtons place at 20 cm mark from NB of the bar. By taking moments about the pivot, find W. So the diagram is this. We are told that the length of the uniform bar is 2 meters. It is, you have NAB. It is pivoted at a distance of 20 centimeters from NA. So this is where you have the pivot. And the weight W is placed 50 centimeters from NA. It is then balanced by placing a weight of 70 newtons. Remember, look at the way I'm drawing the direction of the line of action of the weight. Even if, let me reverse this quickly. I want to illustrate something. Even if you are told that this is just 17 newtons and they did not draw the line of action of the weight, you know weight is a downward force. It acts vertically downwards. It's very important. So whether the weight is just placed there and they did not draw the arrow, whenever you have a force is a vector quantity. It will have both magnitude and direction. So we have represented the weight that is placed 50 centimeter from NA. We have also represented the weight 17 newtons placed 20 centimeters from NB. The question, the weight of the bar itself, has it been represented? Because a uniform bar of length 2 meters and weight 18 newtons. The weight of the uniform bar will be acting where? At the middle. And it will be acting vertically downwards. So the weight of the uniform bar is what? 18 newtons. The weight of the uniform bar there is 18 newtons. Sorry, please, I need to quickly correct something. A uniform bar of length 2 meters and weight 18 newtons is pivoted at 50 cm from NA, where W Newton is placed at 30 cm. So the length of the uniform bar is 2 meters. It is pivoted 50 cm from NA. So this is 50 cm. The pivot is located 50 cm from NA. Then we are told that weight of W Newton is suspended 30 centimeters. So 30 centimeters then weight of 30 newtons is suspended. And the weight of W newtons is suspended 30 centimeters from NA. Remember what I've said. Weight is a vector quantity. So that means that this weight, and it has vertically downwards. So the weight is acting vertically downwards. And it is placed at a distance of 30 centimeters from NA. In order to be more generous with this diagram, the diagram is not to scale. So to be more generous, let me just, so the weight, you have the weight here, W newtons, and I've told you that. Remember, I've repeated that if you have the weight here, you have to draw the line of action of the weight. And the line of action of the weight is acting vertically downward. So that is W newtons. And it's acting at a distance of 30 centimeters from NA. So we have represented all the forces acting on the object. We go over them again. We go over the question again. A uniform bar of length 2 meters and weight 80 newtons is pivoted at a distance of 50 centimeters from NA. So 50 centimeters from NA, you have the weight of the bar. Weight W newtons is suspended at 30 centimeters from NA. The bar is balanced by a weight of 17 newtons placed at 20 centimeters mark from NB. By taking moment about the pivot, find W. So we are representing all the forces. W newtons is 30 centimeters from NA. The pivot is 50 centimeters from NA. 17 newtons weight is 20 centimeters from NB. The weight of the bar itself is a uniform bar, meaning that it has a regular shape and the weight will be acting at the center of gravity. Center of gravity will be at the middle. That's where the weight of the bar itself is acting vertically downward. So we should know that the distance from here to where will be 1 meter, while this distance also is another 1 meter. So taking the moment about the pivot, we have this. This weight is going to cause the bar to turn anti-clockwise from the pivot. This one will cause the bar to turn clockwise from the pivot. This also goes to cause the bar to turn clockwise from the pivot. So we can now write down on there that taking moments about pivot, we have our clockwise moments must be balanced by the what? Anti-clockwise moments. What are the clockwise moments? Remember that moment is the product of the force and the perpendicular distance from the pivot. So we need to know the distance of this force from the pivot. It's acting at 1 meter. Distance from end A to the pivot is 50 centimeters. So distance from the pivot to 80 meters will also be 50 centimeters. Okay? Next, distance of this clockwise moment from the pivot is what? Distance from here to here is 50 centimeters. Distance from here to here is 20 centimeters. That means distance from here to here will be what? 200 centimeters, which is 2 meters, minus 70 centimeters. That is going to give you 130 centimeters. So the distance of the 70 inches from the pivot is 130 centimeters. Because by the time you add everything, I add from here to here is 50, from here to here 180, 20. We've done that. Then the last one, anti-clockwise moment, which is the moment produced by the W Newton's force, is acting at what distance from the pivot? 20 centimeters. Because from here to here is 50, from here to here is 30, from here to here is 20. Once you are able to identify the distance of that force from the pivot, then you can take the moment about the pivot. That's why the distance from the pivot can either be to the left or to the right. That's why you have some moments are clockwise. So the clockwise moment is always, distance is always going in negative x. That's why clockwise moment is taken to be negative moment. While anti-clockwise moment, distance is always going to the positive length. Is taken to be the what? Clockwise moment. But also, that's why we said that algebraic sum of the clockwise and anti-clockwise is equal to 0, which means that the clockwise will be equal to the what? Anti-clockwise moment. So you have to take your distance from the pivot in any given direction. Okay? In any given direction. And you look at the direction of the turning force of the moment. So the clockwise momentum will be, first one is 80 multiplied by 0.5 meters plus 70 multiplied by 1.3 meters is equal to W multiplied by 0.2 meters. I can as well have left the distance in centimeters because I'm not solving for distance. So centimeters is on both sides if you cancel out. But it's good that I put them in meters. 80 times 0.5 will give you 40 plus 70 times 1.3. You do that quickly. 70 times 1.3. 70 times 1.3 will give you 91 is equal to 0.2 times W. So 40 plus 91 is equal to, of course you should know that is 131 is equal to 0.2 W. So W will now therefore be what? 131 over 0.2, which is equal to so that will give you 655 newtons. Okay? So that's it. So look at the basic principle that I've used there. Number one is that we identify the position of the weight of the object is at the middle. We identify the clockwise and anti-clockwise moments. We identify their distance from the pivot, and we took the moment of all the force about the pivot to solve for the unknown. All right.